In this video, we're going to do some examples of Lewis dot structures as seen in the last page of your Lewis dot structures lesson. So what you can do is before we try one, you can pause the video, try it yourself, and see if you're on the right track with what I did. So we'll start with CH4. Always count the number of valence electrons first for your molecule. So it'd be 6 for carbon plus 4 for all the hydrogens total. So that's, 4 for carbon plus 4 for all the hydrogens total. That's 8 electrons total. Place your central atom, place your peripheral atoms connected by single bonds, and see how much you have left at the end. And so we've placed 8 electrons in our single bond, so it's minus 8 electrons, 0 left to place. But it's okay because hydrogen looks happy all the way around, 2 electrons in each bond there. And carbon looks happy all the way around because it has 4 bonds with 2 electrons each, that's 8. Next, we're going to try water. So we have 2 valence electrons from the hydrogens plus 6 from the oxygen. That's 8 valence electrons total. Let's place our oxygen in the center and our H is on the side. We've placed 4 electrons total. So it's 4 electrons left to place. Let's go and fill out our octets for those that need it. Hydrogen's happy, so we just need oxygen. So 1, 2, 3, 4. We're out anyways. Minus 4. Which is 0. We have 0 left to place, but everything's happy. Hydrogen's happy. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So that's our water molecule. Keep in mind this is not the Vesper shape. This is just the Lewis dot structure, so the shape might not exactly match. You'd have to go and find the shape out afterwards using your Vesper table. So let's go to carbon dioxide. Carbon dioxide, we have 4 valence electrons plus 6 6 times 2 plus 12, that's 16 electrons. Let's put our carbon in the middle, our oxygen's on the side, on the peripheries. So what we've done is we've placed 4 electrons. So we have 16 minus 4 is 12 left to place. So we can place those 12 on our oxygens to make them nice and happy. But you'll notice that the carbon is not happy yet. So we need to make some double bonds for them to share, and we get our CO2 like this. And that there's our carbon dioxide molecule. Let's try H2S. So H2S, S has 6, and okay, so 6 plus 2 from the hydrogens, that's 8 electrons to place. We have S, H, H. So we've just placed 4 electrons. There's 4 electrons left to place. Hydrogens are happy. 1, 2, 3, 4. Now we have 0 left, but everything's happy. So we have our complete octet for H2S. Now we'll go ahead and try the NH3. So ENH3. N has 5 valence electrons plus 3 electrons from the hydrogens. That's 8. Let's place our central atom as nitrogen there. We've just placed 6 electrons, so 8 minus 6 is 2 electrons left to place. Our hydrogens are all happy because they have their 2 valence electrons. Nitrogen's not happy yet, so we can place 2 valence electrons on nitrogen, and we get ammonia like that. And once we place those 2 there, there's 0 left to place, but everything's happy. So that was question 5, A through E. Let's try question 10 with some ions. So ClO4. Okay. 10A is ClO4 minus. So we have 7 electrons from the chlorine, valence electrons. From the oxygen, we have 4 times 6 is 24. So plus 24, plus the 1 charge there for the negative, so that's 32. And so we're going to place the chlorine in the center and the oxygens on the periphery. And having done this, we did 32 minus 8, which is 24 electrons left to place. And so we can go ahead and do that as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And so this there would be ClO4 minus. We're not quite done yet because don't forget that this was a polyatomic ion. So we do have to indicate that it's an ion. And the other thing is we can actually draw a better structure than this. So you can leave it like this if you put this, like that, -1. But as I indicated, generally, when you have oxygen in a molecule, you want to have two lines connected to it. Two lines connected to it. How many of those oxygens should have two bonds? Well, if you have a -1 charge over here, what that means is one of the oxygens that's in there will have a single bond and the rest will have a double bond. So let's go ahead and do that. So a better structure for this would be, so this is acceptable, but a better structure is O, like this. And the other ones have one of their pairs turned into a double bond. It does give Cl an expanded octet, but it's able to do that because it's in the third row, so that's acceptable as well. And don't forget to put your -1. That would be a better structure for the ClO4, uh, ion with the double bonds in place like that. It's more stable, and that's really all you need to know for now. Let's do another practice example similar to that. So Cn we've already done in the lesson, a C. Let's try CO3 2-. So we'll do example B here. CO3 2-. So 4 from carbon, 3 times 6, 18 from oxygen, plus 2 from the 2- charge there, that's 24. So we'll place our carbon in the middle and place our oxygens around it. And what we've done here is we've placed 6 electrons already. And so there's 18 left to place. And so we'll do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so we've placed 18. But you'll notice that we're missing some electrons on carbon. So we need to choose an oxygen, any one, and convert that into a double bond. And so we're going to have this. Whoops, let's go back and keep it in the proper position there. We have our single bond over there, double bond over here, single bond over here, and we can put our charges back, 2-. It's okay to have two oxygens single bonded there because our charge is 2- here, so that means there's two oxygens that are single bonded and one that is double bonded. And so that would be an example of a Lewis structure for carbonate. You could have chosen to make the double bond over here or over here instead of at that spot there, and it would have still been a correct answer. They're equivalent structures, and you'll learn more about that in grade 12. Let's try H3O plus, HCO3 minus, and HNO3. Let's try the rest of them there. So I'm just going to erase some of these and stay closer to the top here. You can always rewind if you need to in order to retry or review some of these ones here. So let's remove the ink from the slide. All right. So H3O plus. So we have 3 from the hydrogen plus 6 from the oxygen minus 1 from the plus there. And so that's 9 minus 1, it's 8 electrons. Let's place our oxygen in the middle. Our H is on the side there, or on the periphery. So we just did 8 minus 2 will give you, minus 6 will give you 2 electrons left. The only one that's not happy right now is oxygen, so I'll place our 2 electrons there. Now we're out of electrons and everything's happy. Don't forget to put +1. Let's try for HCO3. That's an sort of an oxy type of acid there. So for HCO3, when we're drawing that, remember that the H wants to be connected to one of the O's. So let's do E here. So 1 from the H plus 4 from the carbon plus 3 times 6, 24 from the oxygen, or sorry, 18 from the oxygen, I should say, because 3 times 6 is 18, plus 1 from the negative sign. That's going to be equal to 24. 24 electrons a place. And so we're going to do COH over here because the H is attached to an O. Then we have our O over here, and then our O over here. And so now what we've done is we've placed 24 minus 1, 2, 3, 4, 8 electrons because we have 4 bonds there. And that's going to be 16 electrons left to place. So we can go ahead and try that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So typically I like to fill out all my peripheral atoms first before I fill out the central one, which is carbon. Notice that carbon is not very happy right now. It's still missing its octet. So I can just take a double bond from one of the atoms somewhere here and put it onto the carbon. Chances are I wouldn't want to take it from this one over here necessarily because it already has 2 bonds connected to it. So I'll take it from an oxygen that does not have the 2 bonds there yet. So it could be from the one on the side there on the top. And so we'll get O, C, O like that, and then O, H. Now everything's happy, and we can put our -1. Let's try HNO3. So we have 1 plus 5 from nitrogen plus 18 from all the oxygens there. That's 24. We'll put N in the middle. We'll put our O's on the side. We'll put our H connected there. So we did 24 minus 1, 2, 3, 4, 8 is 16. So we have 16 electrons left to place. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. However, our nitrogen is not very happy. So we do need to fix that to get a complete octet on the nitrogen. So what we can do is grab a lone pair from one of the oxygens that doesn't already have 2 bonds to it and make it a double bond. And so we get O, 1, 2, 3, 4, 5, 6, N, double bond O here, 1, 2, 3, 4, and then we have OH like this. And so that would be our HNO3. And now we're going to try this for NO+. NO+. So 5 from the nitrogen, plus 6 from the oxygen, minus 1 from the plus. Gives you 10 electrons in place. Let's connect our nitrogen and oxygen together there. And so we get 10 electrons minus 2 in the bond is 8 electrons left in place. So 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is happy, nitrogen is not. So we need to somehow make multiple bonds to make sure that nitrogen's happy. Let's take one of the lone pairs from oxygen and add it to the share there. So we get N, double bond, O, with our lone pairs there. It looks like nitrogen is still not happy, so let's grab another lone pair from oxygen and add that to the share. So we get N, double bond there, or two lone pairs there, triple bond, O, and then lone pairs. Let's put a minus here. And it looks like we are on the right track with that one there because now everything is happy. And we've placed all our electrons where they need to go. So that is the Lewis dot structure for our NO minus ion with a triple bond there. And I believe that would solve that there perfectly. So those are some examples of the Lewis dot structures. We will do a few more examples from extension and 4 in the next video.